Do you know the algorithm behind instant results? That's binary search. Google searches billions of web pages and returns your answer in milliseconds. Without binary search, this would take hours. With it, it takes a few dozen comparisons. Imagine typing a query into Google's search bar. Behind that simple interface, there's a massive database, billions of indexed web pages, all waiting to be searched. If Google checked each page one by one, counting through them sequentially, the counter would tick upward endlessly. 1, 2, 3, 1,000, 1,000,000, and eventually, 1,000,000,000. That approach would take hours, maybe days. But Google doesn't do that. Instead, it uses binary search. With this algorithm, the same search completes in roughly 30 comparisons, 30 steps, to search 1,000,000,000 items. That's the difference between a system that's unusable and one that feels instant. This isn't just a clever trick, it's the foundation of every fast search system you've ever used. And by the end of this video, you'll understand exactly how it works, why it's so powerful, and how to implement it yourself. So how does binary search actually work? Let's build the intuition first, without any code. Imagine you have a sorted array of numbers from 1 to 100, and you're searching for the number 73. Instead of starting at the beginning and checking each number one by one, you start in the middle. The middle element is 50. You compare. Is 73 greater than 50? Yes. So you know immediately that 73 must be in the right half of the array. You've just eliminated half the data with a single comparison. Now you focus only on the right half numbers 51 to 100. Again, you pick the middle, 75. Is 73 less than 75? Yes. So now you search the left half of this new range. You've halved the problem again. You repeat this process, pick the middle, compare, eliminate half. This iterative halving is the key principle of binary search, efficiently narrowing down the possibilities. The search space keeps shrinking. 100 elements, then 50, then 25, 12, 6, 3, 1. Each step cuts the problem in half. That's the core insight. Every comparison eliminates half of the remaining possibilities. This exponential reduction guarantees a rapid discovery of the target, or confirmation of its absence. This systematic approach creates a clear decision path, much like navigating a tree. Each comparison guides the search, ensuring a deterministic route to the target. This structure is what makes binary search so powerful and predictable. It's not magic, it's structure. And that structure only works because the data is sorted. By understanding this integrated system of elimination and decision, you grasp the fundamental efficiency of binary search. Now let's see how this translates into code. Binary search uses 3 pointers: left, right, and mid. Left starts at the beginning of the array, positioned at index 0, and right starts at the end, at index 9. We enter a loop that continues as long as left is less than or equal to right. This bracket highlights the current active search space. In each iteration, mids is calculated as the average of left and right. Let's watch this execute step by step on an example. We're searching for 73 in a sorted array. Then we compare the target value to the element at mid. Since 50 is less than 73, the target must be larger. This means it's in the right half, so we update the left pointer to mid plus 1. Watch how the pointers move, and how the search space shrinks with each comparison. This action eliminates half the remaining elements by adjusting the boundaries of our search. The loop now enters its second iteration, recalculating mid at index 7. This time, the element at mid is 75, which is greater than our target of 73. This tells us the target must be in the left half, so we adjust the right pointer to mid minus 1. For the third iteration, mid is calculated at index 5. Since 62 is less than 73, the target must be in the right half, so left moves to mid plus 1. The active search space is now just a single element. In the fourth iteration, mid is calculated at index 6. If they match, we found it. Return the index. Here, the element at mid is 73, which matches our target. A successful search returns the index, which is 6. The loop continues until we either find the target or the pointers cross, meaning the target isn't in the array. Now let's consider a scenario where the target is not found. Here, we are searching for 99. With each iteration, the search space shrinks, but the target 99 is never located within the array. Eventually, the left pointer crosses the right pointer, indicating the target is not present in the array. The function returns -1. Let's compare binary search to linear search and see why this matters in the real world. With linear search, you check every element one by one until you find the target. For an array of 1000 elements, you might need up to 1000 comparisons. For 1,000,000 elements, up to 1,000,000 comparisons. For 1,000,000,000 elements, up to 1,000,000,000. The time grows linearly with the size of the data. Binary search is completely different. For 1000 elements, you need at most 10 comparisons. For 1,000,000, 20. For 1,000,000,000, only 30. The growth is logarithmic, not linear. Let's visualize this difference. To truly grasp this fundamental difference, we need to visualize how these algorithms scale with data size. We'll plot the number of comparisons required against the dataset size, which we'll denote as n, on a logarithmic scale for the x-axis to accommodate vast differences. On a graph, linear search is a steep upward line. Time increases directly with data size. This represents an order of n growth. For a dataset size of 10 elements, linear search requires 10 comparisons, demonstrating its direct one-to-one relationship with the input size. Binary search is nearly flat. It barely increases even as the dataset explodes. This is characteristic of order of log n growth. In contrast, for 10 elements, binary search requires only about 3.3 comparisons. Notice how it's already significantly more efficient. As we evaluate larger datasets, the number of comparisons for binary search increases only marginally, demonstrating its incredible efficiency even with billions of data points. And this dramatic difference in scaling is precisely why binary search is so critical for modern systems. Mastering this concept is key to understanding efficient algorithms, a fundamental skill for any aspiring professional. This incredible efficiency is why Google can search billions of pages in milliseconds, finding your results almost instantly. Similarly, databases can query millions of rows instantly, thanks to algorithms like binary search optimizing their underlying indexes. And every autocomplete system or efficient search tool you've ever used relies on this principle to process vast amounts of data with minimal effort. It's not just faster, it's fundamentally different. This makes binary search one of the most important algorithms in computer science and a frequently asked question in coding interviews.